Hello! In this video, we are going to prove the following theorem. Let k be an integer and suppose m and n are integers such that m is less than or equal to n. Then, for all lists of real numbers, am through an, we have that the sum from I equals m to n of ai is equal to the sum from I equals m plus k to n plus k of ai minus k. So really, what we're proving here is the shifting index rule for summations. Now to start with the proof, let's give ourselves an integer k and an integer m. And now, we will proceed to prove this by induction on n. That is, we're going to show for all integers n greater than or equal to n, that we have that this is true. So let's start with a base case. Now in the base case, we're trying to prove that this is true for the smallest integer greater than or equal to n. So really, we're trying to prove that this is true for n. Which means we're trying to prove that for all lists of real numbers am, we have that this is true where n is equal to n. So since we're trying to prove a statement about every list of real numbers am, give me an arbitrary list of real numbers an. And now, we want to prove that this sum is true where n is replaced with m. So let me start out by writing the left-hand side. Now, since the lower and upper bounds are equal, this means that this sum is just equal to ai, where we replace I with our lower and upper bound n. So it's just equal to an. But we know that am is equal to an plus k minus k. But now notice, this is really equal to this, right? Because we know that since the lower and upper bounds are the same, this sum is really just equal to ai minus k, where we replace I with n plus k. So really, this sum is precisely equal to an plus k minus k. So as you can see, we have shown that this is equal to this, meaning we have shown that this is true in the case where n is equal to n. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to n, where this is true. The whole goal of the induction step at this point is to prove that this is also true for n plus 1. So really, we're trying to prove that for all lists of real numbers am through an plus 1, we have that this is true where instead of n, we have n plus 1. So give me an arbitrary list of real numbers from am to an plus 1. And our whole goal is to show that this is true where instead of n, we have n plus 1. So to start, let's write this sum where we have n plus 1 here. Now, since n plus 1 is strictly greater than m, we can pull away the n plus 1th term from this sum and rewrite it as the sum from I equals m to n of ai plus an plus 1. But now, we would like to rewrite this sum as this. Can we do that? Well, it turns out we can, because to use our induction hypothesis, well, we have to have a list of numbers from am to an. Well, we have a list of numbers from am to an right here. So, taking this list, we have that this is true. So since this is true, we can replace this sum with this. But then notice, we know that an plus 1 is the same thing as an plus 1 plus k minus k. And in fact, I'm going to swap the order of the plus 1 and the plus k. And I'm just going to put parentheses around that. And now notice, this is really just the n plus k plus 1th term of this sum, right? If you think about all the terms of this sum, the final term in the sum is the n plus kth term. Well, the term that would come after the n plus kth term is the n plus k plus 1th term. So really, taking all of this, we can rewrite it as the sum from I equals n plus k to n plus k plus 1 of ai minus k. And what I'm going to do now is I'm going to swap the order of the k and the 1. and I'm going to put a parentheses around the n plus 1. Because as you can see, we have shown that this is equal to this. In other words, we have shown that this is true where instead of n is replaced with n plus 1. That's exactly what this equal to this tells us. And that was the goal of the induction step. So this completes the induction step. So since we've completed both the base case and the induction step, this means we have closed the induction. Which means we have proven for all integers n greater than or equal to m that this is true. So putting this all together, what we have now is given any integer k and any integer n, then for every integer n greater than or equal to n, this is true. Which means we've proven precisely the theorem, and that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.